So welcome to Study Unit 6, Lecture 2, and in this study unit we'll quickly discuss single-phase controlled thyristor converter circuits. So shown here is figure 12.4 from the text, and it shows a half-wave converter, half-wave rectifier, but the diode is instead replaced with a thyristor. So to go through this again, the output voltage is determined by the trigger angle alpha. This is the angle at which the thyristor turns on and conduction can start, and by the extinction angle beta, which is the angle at which the thyristor will no longer conduct. In other words, it's the angle at which the thyristor turns off. So for this circuit, the output voltage can be generally expressed by writing down Kirchhoff's voltage law for the circuit. So the source voltage is equal to root 2V sine omega t, and this is equal to the voltage which is present over each of the elements in the load. We assume that there is no voltage across the thyristor. So in other words, the output voltage will now be V out of t is a function of the voltage across the inductor, so L dt, plus the voltage across the resistor part of the load, so Ri, and this will be equal to the input voltage. For this equation to hold true, omega t must be between the delay angle alpha and the extinction angle beta. In other words, this is the equation for the output voltage when the thyristor is conducting. The output current as a function of time can be derived by solving the differential equation in terms of di dt. So a generalized solution for the output current is shown here. The I as a function of omega t is equal to root 2v divided by an impedance z, which is defined over here, multiplied by a bunch of trigonometric functions which describe the various angles and the relationships between the angles alpha and theta, where tan theta is given by omega l over r, and alpha is the delay angle and beta is the extinction angle. The extinction angle beta is a function of where the delay angle alpha starts, so it can be solved for using this equation over here. So the easiest way to solve for beta when the variable is inside the trigonometric function is to rather plot beta in terms of the angle theta. Phi. This equation here is plotted here in the top graph, which plots beta minus alpha against alpha, or in more layman's terms, the conduction angle versus the delay angle on the horizontal axis. For this family of curves, there are several curves where phi is put equal to 0, 30 degrees, 45, 60, 75, and finally 90 degrees. And this generates a family of curves which help define how the load behaves. So on the lowness scale here with phi equal to 0 degrees, the load is purely resistive. When phi is equal to 90 degrees, there is no resistive component to the load, and the load behaves as a purely inductive element. Finally, the mean output voltage is simply the mean output current multiplied by R, and is root 2 over V divided by 2 pi minus cos alpha minus cos beta. So the first case that will be considered is for a purely resistive load. This is where the impedance Z is equal to only the resistive component of the load, and angle phi is equal to 0 degrees. With the purely resistive load, the output current simplifies quite nicely to root 2V over R multiplied by sine omega t. In other words, the output current is just a scaled version of the source current. The output voltage is just the average voltage over a cycle, and it's given by this expression here. And solve the integral, use the output voltage as a scaled average output current multiplied by the resistive element, which is root 2V over 2 pi multiplied by 1 over 1 plus cos alpha. From this equation, cos is maximized when alpha is 0, so V out max is 0.45 of V in. For a purely inductive load, the impedance Z, which is seen, is only the inductive part or the reactive part of the load, which is given by omega L. The maximum angle phi is given by pi over 2. So the average output, the output voltage as a function of omega t can be expressed as root 2 V sine omega t. In other words, just as the input signal for when omega t is between alpha and 2 pi minus alpha, and the rest of the time when omega t is out of this range, the output voltage will simply be 0. The output current simplifies to I of omega t is equal to root 2V over omega L multiplied by cos alpha minus cos omega t. An important aspect of a purely inductive load is that the total power delivery is 0, because the energy which is delivered into the inductor, shaded here, is equal to the energy which leaves the inductor in the negative part of the cycle. In other words, for purely inductive load, when the inductor does conduct, the net power transfer to the load is 0. As with many examples where there is a back EMF, conduction only starts when at some new angle or some new delay angle alpha hat, where the back EMF is first overcome by the source voltage before conduction can take place, and this angle alpha hat is given by arc sine of back EMF E divided by root 2V. In other words, the starting angle is given by the arc sine of the ratio of the EMF divided by the square root of 2 of the input voltage. So once again, writing Kirchhoff's voltage equation for the entire converter, the voltage through the loop is simply Ri, which is the output voltage across the resistor, plus the voltage across the inductor, plus the back EMF is equal to the input voltage. If continuous conduction current is assumed, then this differential equation can be solved for dIdt. Once again, to spare my terrible handwriting, I have simply pasted in the actual solution to the differential equation for dIdt. The solution is valid if alpha is larger than alpha hat. In other words, the actual delay angle is larger than the modified delay angle, which is introduced by the EMF, and when omega t is equal to 2 pi plus alpha is larger than 0. If the output current I is always larger than 0, then the circuit will be operating in a continuous conduction mode. But if the output current ever drops to 0 or less than 0, then the circuit will be operating in the discontinuous conduction mode. To derive the solution for the continuous conduction mode, alpha is set to alpha hat. Additionally, if omega t equal to 2 pi plus alpha is larger than 0, then the circuit will also enter into a continuous conduction mode, and this means that continuous conduction can be defined by the following angle relationship, where sine of alpha minus phi is larger than sine of alpha hat over cos phi. Simply put, if this relationship is satisfied, then the circuit will remain in continuous conduction mode. For discontinuous conduction, the just term discontinuous conduction implies that the output current falls to 0, and this can be done by solving for beta when I of beta is equal to 0. The other boundary condition for the solution requires that 2 pi plus alpha be larger than beta, but beta must also be larger than pi over 2. This boundary condition here basically just constrains the extinction angle beta to the second half of the cycle over here. With these boundary conditions in place, beta can be solved for iteratively through application of this equation here. Finally, during discontinuous conduction, in the presence of a back EMF, the back EMF must be accounted for in the output voltage equation. And this can be done with this expression here, where the output voltage is the input voltage between 0 and the extinction angle beta, plus whatever the contribution is from the back EMF from beta to 2 pi plus alpha. The average output current is given by the output voltage, subtract minus the back EMF divided by the output resistance, which can be expressed as VO minus root 2 V sine alpha hat of R. This can be expanded to write the output current as root 2 multiplied by V divided by R divided by 2 pi multiplied by cos alpha minus cos beta plus pi plus alpha minus beta times sine of alpha hat. Mathematics aside, it's important to notice, or to take note, that depending on the conduction and extinction angles and the type of inductance used, there will be continuous or discontinuous conduction in the converter circuit. Whether or not the conduction type will be continuous or discontinuous is something which is important to note during the design phase of any such half-wave rectifier circuit. And that concludes this lecture.